All right, this is day 5 of our unit 6. Today we're going to talk about normal distribution and the curve and how to create a normal distribution chart. It's almost kind of like when we did the it's good like when we did the box and whisker plots, except for you're going to use your standard deviation instead. So this is what a normal distribution chart looks like. It's shaped like a bell shape and it's symmetric on both ends. So that's when that's what you like to see whenever your data is very well separated. Positively skewed means your data is tall and the tail is to the right, or my bump is to the left, okay, that's positive. This is a negative one where everything's to the right end of our graph. But most of the stuff we're talking about is a positively skewed right here. So everything that we're going to be doing today is creating this normal curve and being able to answer questions and all that good stuff with it. Okay, so whenever you create this line right here, this number that you're going to use is always going to be your mean. Okay, and remember your means when you add up all the numbers and divide by however many there are. And I also showed you a calculator trick on how to do that, and I'm going to use my calculator most of the way. I'm sorry if you don't have a calculator at home, because you are going to use standard deviation with this. Like I said, there is a way to do standard deviation with the calculator. If you don't have a calculator, like I said, there is a option with TI-84 where they're doing it online for free for 90 days, I believe. So you just look up TI-84 online and they've got a 90-day trial for you to be able to use the calculator. Okay, so what we're going to do here is this is going to be your mean. Okay, and then each one is a standard deviation off. So like here, this would be positive 1 standard deviation. And remember, this little circle with the line on top is equal to your standard deviation. Okay, now, so that means because this is 1 standard deviation away, that means this is 2 standard deviations away. So it's a positive 2 standard deviations away. Okay, and then the rest of this would be 3 standard deviations away. The vast little section here, 3 standard deviations, okay? Which means that on the opposite end it's the same, but instead of adding it, you would subtract it. So that's minus 1 standard deviation, okay? Minus 2 standard deviations, and then minus 3 standard deviations, okay? So now this helps us immensely right here, because this is going to tell us the percentage of which our data is going to lie within the mean. So whenever you talk about 1 standard deviation, each side has about 34% of your data. Okay, so that means that if you add that up, that means that 68% of your data falls within 1 standard deviation of the mean. So between 1 standard deviation of your mean, 68% of my data is here. That's why the hill is so tall up here, because that means that's holding the majority of your data. Okay, the next section is going to have about 13.5% of your data. So both of these have about 13.5% of your data between 1 standard deviation and 2. Okay, which means if I add this entire thing up, about 95% of the data lies within 2 standard deviations. And you can check that. You can do 34 plus 34 plus 13.5 plus 13.5, and that gives you that 95%. So 95% of my data lies within this, okay? And this will help us, because it might ask you, like, you might know this number, and it'll say what percentage of your data lies between those 2 points, and you'll say 13.5, or you'll add up the rest and that type of deal, okay? And then the next percentage is 2.35%. is within this little teeny tiny space right here. And same thing here, 2.35%. And if you add all those percentages up, that gives you 99.7% of your data. So there's going to be like a little bit off within your answers and stuff like that, but 99.7% of your data lies within 3 standard deviations, okay? And so that will help us with being able to find all that good information. So we've got 2 different data sets, and I want to be able to create the standard deviation and my normal curve of those, okay? So looking at my data set 1, Whenever you do that, the first thing you need to be able to find is your mean and your standard deviation. I'm gonna put SD for standard deviation. We need to know what those two numbers are so we can create our curve. And I taught you how to find this, and I'm gonna go over it again, okay? You go to Stat, Edit, and I'm gonna clear out this column by hitting Clear Enter, okay? And then you type in the first data set. So we've got 4, 8, 5, 12, 3, 9, 5, 2, okay? And then you hit Stat, go over to Calc, and then you hit that one variable stats option. And so there, that first number, remember the X with the bar over it also stands for your mean. So 6 is my mean. And then my standard deviation is this number right here, my little standard deviation symbol, 3.16, okay? So to create our bell curve, I'm gonna kind of sketch what this looks like, okay? Y'all know not to judge my drawings. Okay, so the middle of that curve is always our mean. So that means my mean right here is 6. Okay, one standard deviation away from that, it means that I'm going to add that 3.16 or subtract it to both ends. So I'm going to do 6 plus 3.16, and that gives me 9.16. Oh, yeah, 3.6 plus 3.16, okay. So 6 plus 3.16, just checking behind myself for a second. So that gives me 9.16 here, okay? And then I'm going to subtract 3.16 to get my other side. So 6 minus 3.16 gives me that 2.84, okay? So that means all of my data lies between these two numbers, or not all of it, but 68% of my data lies between those 2 points. And then our second standard deviation means we're going to add that 3.16 and subtract it twice. So I'm going to do 6 plus 3.16 plus 3.16 again to give me that this is 12.32. And then if I want to go ahead and fill out that last column, I can go ahead and just add 3.16 again to get that my final answer over here will be 15.48. So that's 1, 2, 3 standard deviations away. Then I would subtract again and subtract those other two. So 6 minus 3.16 minus 3.16 gives me my second standard deviation will be negative 0.32. And then subtract 3.16 again to get negative 3.48, okay? So you've created a normal distribution curve at that point, okay? All it is just taking that mean and adding and subtracting that standard deviation however many times away from it you are, okay? So let's do this again with our second data set, okay? So that's data set 1. This is data set 2, okay? So we'll take Stat Edit, and we'll fill in our points again. So 5, 9, 11, 4, 6, 11, 2, and 7. So that becomes Stat Calc. Go to our one variable stats. And my mean is equal to 6.88. And then my standard deviation, SD, is 3.06. Okay? So again, 6.875, 3.06. Okay, so that means right here in the middle, we'll have 6.88. And then we'll add 3.06, 1, 2, and then 3 times at the end. So 6.88 plus 3.06 gives me 9.94 plus 3.06 gives me 13 plus 3.06 2.06 gives me 16.06. And then again, we'll do the same thing, but we're gonna subtract 1, 2, and then 3 times, okay? So that gives me 6.88 minus 3.06 gives me 3.82 minus 3.06 gives me 0.76 minus 3.06 gives me negative 2.3. Okay, so that is another example of finding our standard deviation and all that good stuff. Remember, the standard deviation one was where we had to find the mean, then subtract our mean from each data point, square it, add all those numbers up, and divide by how many numbers we are, and then square root that. So I'm just kind of using the shortcut way by using the calculator. But again, if you don't have a calculator, unfortunately, you're going to have to do the long way to do that. Okay, so that's 1 and 2. And then let's do the next 2. Okay, so we got our data set, stat, edit, and we've got our first points, 102, 98, 103, 86, 101, and 110. And then I've got a few more data points on what I want. All right, and then we hit Stat Calc, go to our one variable stats, and then we got that so for data set 1, our mean is equal to 100, and our standard deviation is equal to 7.23. Okay, so we'll create our little standard deviation curve here. Okay, our mean is right here at 100, and then we're going to constantly add by 7.23 3 times. Okay, so 100 plus 7.23 gives me 107.23 plus another 7.23 gives me 114.46 plus 7.23 gives me 121.69. Okay, and then we'll do the same thing, except for we're going to subtract. So 100 minus 7.23 gives me 92.77. Minus 7.23 gives me 85.54. Minus 7.23 gives me 78.31. So that's saying that all my data points should lie somewhere between these points. And then you've got your first section, which is 30 or 34 and 34. So that's 68% of my data should lie within there. And then the 13.5 and then the 2.35 in each one of those two. Okay, and we'll do some examples where we answer problems actually about that here in a minute. All right, so then let's do another one. We got our data set 2. Okay, using our data set 2, again, we go stat edit and we fill in our points, 90, 89, 100, 97, 102, and 97. All right, and then we hit stat calc, go to our one variable stats. And so our mean is 95, so data set 2. Our mean is equal to 95.83, and then our standard deviation is 4.81. Okay, so for our middle point, that's that 95.83. And then here, we're going to constantly add 3 times to get our other 3 points. So 95.83 plus 4.81 gives me 100.64 plus 4.81 gives me 105.45 plus 4.81 gives me 110.26. And then again, we're going to subtract on the other side, 1, 2, 3 times. So 95.83 minus 4.81 gives me 91.02. Minus 4.81 gives me 86.21. And then minus 4.81 again gives me 81.4. All right, so that's our whole standard deviation curve for both of those two data sets. And remember, the smaller the standard deviation, the less spread out our numbers are. So remember that 4.81 means that my numbers are much more together than what the 7.23 standard deviation is. That means my numbers are a lot more spread apart, which doesn't tell me much about our data, since you always want, if you're like looking, the whole reason we use these curves and stuff like that is to be able to understand something and be able to make a prediction. And so if it's more spread out, that means it's less random, or it's more random, and it's less likely to be able to make a prediction. Okay, so then on this number 3, again, we're going to do the same thing, finding our standard deviation with our data set. Okay. So with data set 1, again, we need to find our mean and our standard deviation. So we hit stat edit, and we plug in our points. So we've got 32, 40, 35, 28, 42, 32, and 44. And then we hit stat, go over to calc and hit that one variable stats again. And we've got that our mean is 36.14 and our standard deviation is 5.51. Okay? So that means that 36.14 is in the middle. And we add 1, 2, 3 times. So 36.14 plus 5.51 gives me 41.65 plus 5.51 gives me 47.16 plus 5.51 gives me 52.67. Okay. All right, and then for the next side, again, we're going to subtract 1, 2, 3 times, okay? And so we're going to do 36.14 minus 5.51, which gives me 30.63 minus 5.51 gives me 25.12. Minus 5.51 gives me 19.61. All right. So that's our normal curve, our normal distribution curve written there. We got one more example where we're drawing it out. Okay. So again, with data set 2, we need to find our mean and our standard deviation. So we hit stat edit and we enter our new point. So we got 40, 38, 51, 39, 46, 40, and 52. And again, we hit stat, go over to our calc, one variable stats. And then you hit that our mean is 43.71. And then we get that our standard deviation is 5.47. Okay? So we create our curve. And our mean is right there in the middle. And we have 43.71. And again, we're going to be adding by 5.47 3 times. So 43.71 plus 5.47 gives me 49.18 plus 5.47 gives me 54.65 plus 5.47 gives me 60.12. And again, we're going to subtract 3 times to get our other 3 points. So 43.71 minus 5.47 gives me 38.24. Minus 5.47 gives me 32.77. And then minus 5.47 gives me 27.3. Okay, and again, data set 2 this time has a smaller standard deviation. Even though it's not by much, it still has a smaller standard deviation, which means that it has the closer data points. It means that our numbers aren't quite as spread out as the first data set. Okay, so then let's move on to the next page. All right, and I'm gonna be going through some. I might cross out a few examples because there's some problems that's more calculus that I'm not gonna give you. Okay, so we've got that the height of 1,800 teenagers are normally distributed with a mean of 66 inches and a standard deviation of 2 inches. About how many teens are between 62 and 70 inches? So first thing I always do with these types of problems is I just go ahead and draw the curve out because it gives you all the information you need. Okay, so I've got my curve and it says that the mean is 66 inches. So 66 is right here. And then we've got a standard deviation of 2. So that means I'm going to add 2 3 times. So that's 68, 70, and then 72. And then subtract 2 inches. So 64, 62, and then 60. So all of my students are somewhere between 60 and 72 inches. Okay. It asked me about how many teens are between 60 and 72 inches. So that means it's asking from the 62 to 70 inches. So it's asking for this 2 standard deviations plus these 2 standard deviations. So remember, that's going back to that very first page in our notes where it says, because notice it's asking for here all the way to here. So that's 2 standard deviations on both sides. And if our data is 2 standard deviations, we talked about that's 95% of our data. So 95% of our students are between 62 and 72 inches. Now, it's not asking the percentage, it's asking how many. So what you'll do is we'll take our total teenagers, which is 1,800, and we're going to multiply by our percentage, which is 0.95. So 1,800 times 0.95 gives me that 1,710 of those students are between 62 and 70 inches because that's 95% of the data. So that makes sense for it to be almost the whole entire thing. Okay? And then letter B, we're going to cross out because we're not going to do anything with probability here. And then scooping down to here, it says the grade point averages of 1,200 students at East High School are normally distributed with a mean of 2.6 and a standard deviation of 0.6. Okay, so first of all, that's a really low school if the mean is 2.6. You want a higher mean of a GPA than that, but whatever. Anyways, it says how many students have a GPA between 2 and 3.2. So let's draw our little curve again. Okay. And so we have our mean is 2.6 and our standard deviation is 0.6. So 2.6 plus 0.6 gives me 3.2, I believe. Yep, 3.2 plus another 0.6 gives me 3.8 plus another 0.6 would give me 4.4. All right, and then we'll do the same except for subtracting our 0.6, so that would be 2.0, and then 1.4, which would give me 0.8. So our GPA would be somewhere between 0.8 and 4.4 in the school, okay? Now we want to know between 2.0 and 3.2. So if you take your mean, that's going out 1 standard deviation this way and out 1 standard deviation that way. So it's going out one standard deviation in both directions. And again, if you go back here, one standard deviation, that's 68% of your data, okay? Now, say, for example, the question asked for like 3.2 to 4.4. What you would do is you would take these two percentages, this standard deviation and this one, take those percentages and add those two up. So we're just lucky that these are connected to each other. So that's 68% of my data, so 68%, because that's 34%, and that's 34%. And same thing here, 34, 34, and 13.5, and 13.5. So if you took all those percentages and added them up, that would give you that 95%. So 68% of my data are between those 2 points. So that means I'm going to take 1,200 students and I'm going to multiply by the 68% or 0.68. Okay, so 1,200 times 0.68 gives me 816 students would have between a 2.0 and a 3.2. Okay, and again, letter B we're going to cross out because we're not doing anything with probability. And just a reminder again, this asks for how many. Now, if it gave you just asking what the percentage of students would be between 2.0 and 3.2, all you have to do is add those percentages up and you would just say 68%. Okay? All right, so then we need to talk about z-scores. Okay, a z-score reflects how many standard deviations above or below the mean a raw score is. The z-score is positive if it's above the mean and negative if the value is below the mean. Okay, remember X is just your data point. Then the X with the bar over it is your mean. And then this little circle thing right here is your standard deviation. And we'll use that to be able to either find our z-score or to be able to use that to find what our mean is or anything like that, or what their actual score was. So for example, one, we have suppose SAT scores among college students are normally distributed with a mean of 500 and standard deviation of 100. If a student scores 700, what is her z-score? Okay, so it gives us that our mean is 500 and our standard deviation is 100. We want to know if the student scores a 700. So that's our data point right there. What is her z-score? So we're looking for z. Okay, so z is equal to our actual data point, which is 700, minus our mean, which is 500, over our standard deviation, which is 100. Okay, so we would do 700 minus 500 over 100 to give us that her z-score is 2. So that means she is 2 standard deviations above the mean, which means that her score is above what most or the average of somebody else's score is. So that would be really good if she got a standard deviation of or a z-score of 2. Okay, the higher the z-score, the better your score is, because that means you're in the higher percentage of what somebody else did. Okay. Number 2 says if Harold's math class has a recent test and has a mean of 70, okay, we got a mean of 70 and a standard deviation of 8. In Harold's English class, his test has a mean of 74 and a standard deviation of 16. If he earned a 78 on both tests, which subject is his performance better? So we need to find the z-scores of both those tests so we can determine which one he did better in. Okay, so we're going to look first at his math class. Okay, so his z-score is, he made a 78, so that's his data point, minus the mean, which is 70, divided by our standard deviation, which is 8. Okay, so 78 minus 70 just gives us 8, divided by 8, which is 1. So he's 1 standard deviation above what the mean is. Okay, so then let's look at his English test score. And his English test score, he scored again a 78. And the mean of the test was 74. And the standard deviation was 16. Okay? So that means we're going to do 78 minus 74 over 16, which gives us a 0.25. So he was only 0.25 standard deviations above the mean in his English class, which means that his math class is the class that he did better in. That's the better test score, because he did a higher Z-score than what his English test was. This Z-score is really good about comparing data points from two different tests, because their standard deviations and their means are different, but you're able to tell who does better in what. Okay? So then, for example, we have some adult height. We've got their shoulder width and their height, and we've got it separated by male and female and what their mean and standard deviations are. Okay? So number 8, the first example says, how tall is a male with a Z-score of 1.6? So this time we have the Z-score, so it's equal to 1.6. We don't know how tall the male is, so we're looking for X, because we know what the mean is. Okay, the mean score of a male for his height, if you look mean male, that's 68.8. And then the standard deviation of that is 2.65. So we want to be able to solve for what our actual data point is. We need to find out how tall he is. All right, so what we're going to do is solve for X, and you'll multiply by 2.65 to both sides. So 1.6 times 2.65 gives me 4.24 equals X minus 68.8. And then you'll just add 68.8 to both sides. So that means that our male is 73.04 inches tall. Okay, 73.04 inches tall. All right. The next example says, if a female is 5 foot tall and the male has a Z-score of 0.03, who is relatively taller and who is actually taller? So relatively means their Z-score, who's taller relatively, versus their actual height. We're going to compare, so that means we're going to have to turn our male's Z-score back into his actual height. Okay, so our female, we know, is 5 foot 5 inches. Okay, so we need to find her Z-score. So her Z-score is equal to her actual height. Now notice we're talking about inches. So we've got her height in 5 foot 5 inches, which means we need to turn it into a total of inches. All right, so there's 12 inches in a foot, so she's times that 5 foot, plus that extra 5 inches means that she's 65 inches tall. Minus the mean of our female heights, which is 63.6, divided by our standard deviation, which is 2.5. Okay, so 65 minus 63.6 divided by 2.5 gives that her Z-score is 0.56. Okay, so her Z-score is 0.56. And then, so then we've got our male. We know that his Z-score is equal to 0.3, okay? But we don't know what his actual height is, so we're gonna solve for that. So 0.3 equals his height minus the mean, which is 68.8, over our standard deviation, which is 2.65. All right, so we're going to multiply by that 2.65 again. I'm not going to show all of that word just because I don't have a lot of space. So 0.3 times 2.65, and then we're going to add the 68.8 to both sides. Gives me that his actual height is 69.595 inches tall. Okay, so based off of their Z-score, that means the female is relatively taller. Okay, so we would say that our answer, relatively taller, is the female. Okay, she's relatively taller because her Z-score is higher than the male's Z-score. Okay, but with our actual height, the female is 65 inches tall, the male is 69.5 inches tall, so that means the male is actually taller. okay? And the reason why there are two different answers is because relatively means that she's relatively taller than most females compared to he's not as relatively taller than other ones. But comparing them together gives their actual height, okay? Then we've got an example where we got Jimbo, a male, has a standardized value of that's supposed to be a negative 1.2 for shoulder width. Can he walk between two poles that are set 16.5 inches apart without turning sideways? So we need to look at his shoulder width this time. Okay, we know that his z-score is negative 1.2. Okay, we don't know what his actual shoulder width is, so we're going to label that as x, minus the male shoulder length, because obviously it says Jimbo's a male, 17.7, over the standard deviation, which is 0.85. All right, and we're going to solve just like we've been doing. We're going to multiply by 0.85 to both sides. So negative 1.2 times 0.85 gives me negative 1.02 equals x minus 17.7. And then we add 17.7 to both sides. So that means x is equal to 16.68. Now it tells us that the poles are 16.5 inches apart. Well, his shoulders are 16.68, which means that the answer is no. He will not be able to fit without having to turn sideways at least a little bit. Okay? Then the next question asks what percent of women are taller than 66.1 inches. So that's when I like to actually draw the standard distribution graph. Okay? So we're going to sketch it out. We've got that the actual height of women is 63.6. That's their mean. And then we're going to add by the standard deviation to both sides, or add and subtract to both sides. So 63.6 plus our standard deviation, which is 2.5, gives me 66.1. And then plus 2.5 again, which is 68.6. I don't have a lot of space to write this out. Plus 2.5 again gives me 71.1, okay? And it's actually asking how many are taller than 66.1 inches. So we don't even need what's back here. We need everything that is above 66.1, okay? And so just a reminder, remember that means that this is, if you look back at the very beginning, my first section is 34% of my data. The next one is 13.5. And then the next one is 2.35. We want above that 66.1%. So we need to add these two percentages up, which is 13.5 plus that 2.35%. Okay, when we add those percentages up, that means that 15.85% of my women are above 66.1 inches. So we didn't even need the back half because we wanted to know what was above that 66.1. That's why I didn't even write it out, because I didn't need it. I needed what was above it. So you have to add those percentages up. All right. The next example says how tall is a male with a standardized value of 2.3. So we know that his z-score is equal to 2.3. And we need to know what his actual height is. So that's going to be x minus the mean, which again is 68.8. And then divided by our standard deviation, which is 2.65. And again, to solve, we're going to do 2.3 times 2.65, which gives me 6.095 equals x minus 68.8. Then we'll add the 68.8 to both sides, so that gives me x is equal to 74.895. So he's about almost 75 inches tall. Okay, and that would be our answer there. All right, three more questions and then we're done. It says, what range of heights represents approximately 68% of women? So remember, if you remember back up here, 68% of my data falls within one standard deviation, okay? So that means I just need to know what heights are between that one standard deviation for my men. So remember, the mean for men is 68.8. and then we need to add and subtract by 1 standard deviation to know what that whole 68% of data would be, okay? So we're gonna take 68.8 and add by our standard deviation, which is 2.65, which gives me 71.45. And then we're going to take 68.8 and subtract 2.65, which gives me 66.12. So that means between 66.12 inches and 71.45 inches, that's 68% of my men. That's how 68% of my men fall within that range of heights. Okay? And then the next question says, how tall is Jenny if 2.5% of women are shorter than her? Actually, no, I'm not doing that problem. Let me skip to the next one. I meant to skip that one. All right, 95% of male badminton players are in the top 16% of height. This means that 95% of male badminton players are at least how tall? Okay, so we need to know. Remember, if you look back here, this 13.5 plus the 2.35, that adds up to almost a full 16%. They're in the top 16%, which means that we need to find out what those top 2 standard deviations are. So that way we can find out how tall those top 95% of our badminton players are. Okay, so if we look, our mean height is 68.8 again. 1 standard deviation is 71.45, and then if we add 2.65 again, gives me 74.1. And so that means we need to know, remember it's the last 2 standard deviations. We need to know from our 1 standard deviation and forward. So it's asking at least how tall are they, okay? So that means we need to know from here to here, the least height is right here because it's just going to get larger and larger. They're just going to keep getting taller from up to 3 standard deviations. So that means the least height that they can be is at 71.45 inches. Okay, if it asks what the range was, you would add your standard deviation 1 more time to get 76.75, and you would add, say that was the range. Okay, so that's the least height. If it asked you the max height of how tall they probably are, it would be about 76.75 inches tall. Okay, so that's the notes for normal distribution curve. Just to look over the classwork examples, you're just going to follow the normal distribution curve. Again, I highly suggest if it asks you about percentages for you to draw the graph out yourself to help you with answering those questions, because a lot of these questions ask you what percentage of people are between certain heights and certain whatever, okay? And then on your next page, I accidentally put in your classwork the same problems we just did. So when you get to this page, actually, you don't have to do any of it because we already did those examples together. Okay, so that second page you don't have to do because I accidentally used the same examples twice. And then the last page, I need you to cross out all of 14 and 15. So you just need to do 11 through 13 on that page. So you only do 11 through 13. 14 and 15 you don't have to do, okay? And then the next thing we'll talk about is statistics and sampling. We'll talk about that on the next day's video. Okay, remember, if you have any questions, message me on Remind 101, email me, comment on the videos, or comment in Google Classroom and let me know if you have any questions at all. All right, bye.